Hi everyone, my name is Jason Cramer, and today I'll be presenting our paper titled Chirping Up the Right Tree, Incorporating Biological Taxonomies into Deep Bioacoustic Classifiers. This work is a collaboration between myself, affiliated with NYU, Lostanlen, affiliated with NYU and the Cornell Lab of Ornithology, Andrew Farnsworth, affiliated with the Cornell Lab of Ornithology, Justin Salamon, affiliated with Adobe Research, and Juan Pablo Bello, affiliated with NYU. So let's start with some motivation. Due to phenomena like deforestation and climate change, the habitat of many migratory birds are threatened, but tracking these migratory changes can help in conservation efforts. So how do we track these birds? One way is through bird watchers, who visually identify birds by species, which provides wide geographical coverage, but is limited to bird sightings that occur during the daytime, and is further limited by availability, capability, and interest of the bird watchers. We can also use weather radar data, which can track avian biomass at high spatiotemporal resolution, but tells us nothing about the types of birds present. However, we can also use audio obtained from autonomous recording units, which provide continuous coverage that can be used for automatic detection and classification using machine listening methods. One practical use case of the latter method comes in the form of the BirdVox project, which is a joint collaboration between NYU and the Cornell Lab of Ornithology. In this project, the goal is to estimate the composition of bird species in a given area to learn about migration patterns, which is done with a network of autonomous recording units and a machine listening system that decouples flight call detection and classification. Machine listening often relies on class hierarchies, which can help us characterize and organize sounds in an acoustic scene. Examples of such taxonomies include those used in AudioSet and the Sonic Urban Sound Tagging dataset. A feature of many of these hierarchies is that they tend to be based on subjective similarity judgments that can vary by culture or use case. On the other hand, hierarchies found in evolutionary biology are formulated through more systematic methods. Using Darwinian classification, we obtain a systematic phylogenetic hierarchy based on the principle of last common ancestor. And we can try to leverage these biological taxonomies in the context of bioacoustics. The main idea that we propose in this work is to leverage biological hierarchies to impose inductive bias on bioacoustic classifiers in order to make more effective use of the data. In particular, we achieve this using multitask training and hierarchical model architectures. The benefit of this approach is that we can encourage the model to learn hierarchical relationship between classes. And additionally, in many conservation science studies, it is not always known which level of the hierarchy provides the most insight for analysis. As such, it is useful to be able to predict at multiple levels with a notion of confidence for each level. Since we aim to train a model end-to-end to jointly predict at multiple levels, it means that we only need to train one model instead of multiple models. So for this work, we use the following taxonomy, which is split into 3 levels: 1 order, 4 families, and 14 species, referred to henceforth as the coarse level, medium level, and fine level. At each level, we have an other class, where all out-of-vocabulary classes are mapped. We adapt the model architecture presented by Salamon et al. In their state-of-the-art work on flight call classification, consisting of 3 convolutional blocks followed by 2 fully connected layers. For simplicity, we henceforth refer to the convolutional part of this network as CNN. In this work, we present a new architecture called TaxoNet. The main idea is that different layers of the network correspond to representations of different levels of the taxonomy, with predictions for each level being output at the corresponding layer. While the ordering of these layers corresponds to the ordering of taxonomic levels, the layers themselves are also structured to reflect the corresponding taxonomic level. The feature maps produced by each layer, which are associated with a level in the taxonomy, are partitioned such that each partition is mapped to a member of the current taxonomic level. For example, here we have a medium level feature map, which is divided into partitions corresponding to families such as thrushes and warblers. Each partition in the feature map that the current layer is only connected to partitions in the subsequent layer that correspond to taxonomical descendants. For example, the thrush partition is only connected with the Swainson's thrush and gray-cheeked thrush partitions, but not the mourning warbler or Canada warbler partitions. As such, the feature maps are hierarchically connected in a way that naturally reflects the structure of the taxonomy. Additionally, each partition is mapped to a multi-label prediction using a fully connected layer with ReLU and Tanch nonlinearities. The other class prediction is computed as the complement of the most likely in vocabulary class. We use multi-label prediction in order to decouple the feature maps between different members of the taxonomic level. The goal of this decoupling is to ensure the specialization of these feature maps to the corresponding taxonomic elements. For training and evaluating these models, we introduce two new datasets. For training and validation, we use what we call the American Northwest Avian Flight Call Classification Dataset, abbreviated as ANAFCC. It is an aggregation of multiple existing datasets which are verified and re-annotated. For testing, we use what we call the BirdVox-14 species dataset, abbreviated as BirdVox-14SD. It is sampled across a full migration season and is annotated for 14 species and other. Both of these datasets are available for download on Zenodo. Finally, we enforce consistency between distributions of species across the testing, training, and validation splits using a knapsack solver. Our training pipeline is as such. For the input to our models, we use log-scale Mel frequency spectrograms and apply per-channel energy normalization, also known as PSEN, with parameters chosen using prior work on flight call detection. The use of PSEN helps to suppress background activity such as insects and highlight sparse events such as the flight calls of interest. We then apply data augmentation using common techniques for audio, such as pitch shifting, time stretching, and the addition of background noise. The training data is then uniformly sampled with respect to the fine level classes. We then use equally weighted multitask training to train our models to predict at multiple taxonomic levels. And finally, we evaluate our models using micro-average accuracy. So to evaluate these models, we compare with baseline models that are only trained to predict at a single taxonomic level. We employ two strategies with these models. The specialist strategy, where at a target level, we predict using a model trained at the same level. And the coarsening strategy, where at a target level, we predict using a model trained at a finer level and project up the hierarchy to the corresponding level. For our fine level prediction results, we first see that TaxoNet outperforms the specialist baseline at the fine level, which shows that leveraging hierarchical classification improves performance even if we only care about the finest level. Looking at medium level predictions, we see that TaxoNet still outperforms the specialist strategy. We also see that TaxoNet significantly outperforms the coarsening strategy. This shows us that TaxoNet is capable of multitasking, as well as providing more consistent results than the coarsening approach. Finally, looking at the coarse level, we first have to note that there's severe class imbalance, which makes the problem much easier than at finer levels. Nonetheless, TaxoNet matches the specialist strategy and coarsening strategy from the medium level, and it also significantly outperforms the coarsening strategy from the fine level. So overall, we've seen that with hierarchical architectures and multitask training for hierarchical prediction, we can match or outperform the specialist models at all taxonomic levels. This means that we can train a single model to perform at least as well, if not better, than multiple single models trained to do the same job. Our approach also matches or outperforms coarsening strategies at all taxonomic levels, meaning that our model tends to make less glaring mistakes than over-specific models. We also performed some ablation studies to explore some of the design choices of TaxoNet. First, we look at a non-hierarchical multitask model where we still jointly train the model to predict at multiple levels, but the structure of the model is not modified to reflect that of the taxonomy. We also look at a variation where we don't partition in the feature maps according to the taxonomic levels, and instead have a joint representation across each taxonomic level. We also looked at a model that is very similar to TaxoNet, where we replace the fully connected layer in between partitions and the classification activations with a mean. The goal here is to simplify the way the feature maps are aggregated and give more representational responsibility to the feature maps. Finally, we look at another slight modification of TaxoNet, where we explicitly model the other class and replace the 10H nonlinearities with a softmax, thus coupling the feature maps for each class. This changes the training formulation from multilabel to multi-class. Comparing these ablations, we first see that TaxoNet performs best across the board at the fine level, while performing second best at the medium level. Unsurprisingly, all ablations perform similarly with TaxoNet at the coarse level. Looking at each ablation compared with TaxoNet individually, we first see that not incorporating hierarchical structure in the model results in degraded performance. When we use hierarchical structure without partitioning the feature maps, we also see degraded performance, especially at the fine level. From these first two ablations, we can say that hierarchical structure and partitioning are both important for improving classification performance. When replacing the connections between feature partitions and classification activations with simple averages, we see that we have an improvement at the medium level, but a degradation at the fine level. The reason for this is not entirely clear, but it could be because the averaging of rectified features with tanh applied yields 0 only when the features are 0, which implies that all descendant partitions are also 0. While this may ideally be a desirable feature, it may make fine-level classes harder to learn. Finally, we see that using a multi-class formulation with softmax activations results in degraded performance. This could be because the resulting coupling between representations causes the partition feature maps to become less specialized. So in summary, we've shown that TaxoNet matches or outperforms specialized and coarsening strategies using single task models, meaning that deep hierarchical classification can exploit taxonomic relationships to better leverage training data. We also introduced 2 new data sets, ANAFCC and BirdVox-14SD. We've also released some of our models in a Python package, BirdVox-Classify, which is integrated in the most recent release of BirdVox Detect, a flight call detection package, which can be installed via pip. As far as future work, we didn't enforce any consistency between predictions at different levels of the taxonomy, but this is useful not only for practical uses, but also for potentially improving model optimization. More generally, we can also explore the effect of depth and width of the taxonomies for training hierarchical models like TaxoNet. You can check out our code on GitHub, and last of all, thank you very much.